Okay, in the previous video we have studied relations, and we defined relations as a mapping from one set to another, and it was such that one element from first set was mapped or linked to another element from the second set. And we also saw that relations could be expressed in many different ways. We saw that relations could be expressed as a set of ordered pairs, or they could be expressed in set builder form. We also saw that they could be expressed in graphical form, and we also looked at arrow form. All this is a fancy definition of relation, but relations is nothing but a way of connecting two variables. So we have a ordered pair of variables, and those variables can have different values, and they are related in some way. And sometimes the relation is given in the form of an equation, so that can also be used. Now in this video we are going to talk about functions. Now functions are a special kind of relation. So what happens is that if you have a function in which every element from the first set is related to some element in the second set, and then every element of the first set should be related at most to one element of the second set, then this relation is known as a function. I think it would be better if I write this here. So let me write it here. I think that will make sense. A relation is a function if, so there are two conditions that are to be met. I could combine the two conditions and write them in one sentence, but I think I will split them in two and write them so that it makes more sense. So first is that every element of set A should be mapped to some element of set B. Yeah, it's simple. When you look at it, it has got interpretation, and you can interpret this in terms of domain as well. So let me pull it a little bit down here. Yeah, so we can interpret this condition in terms of domain as well, because we know that domain is a set of all the first elements of a relation. So it means that the domain of the relation should be set A. So whole of set A should be in the domain, which means every element in the A should be related or mapped to some element of set B. And second condition is that every element of set A should be mapped at most to one element and element of B. Now this is a important condition, and as I told you, we could combine these two and make them one, but it makes more sense to split these two conditions. Now let's look at some examples now. So let's look at this relation which I have, and it's in the roster form. So I'll write it like this, and 3, 5 and 4, 5. Do you think it is a relation? Do you think this relation is a function? So pause the video here for a moment and try to examine this relation by using these two conditions, using this criteria here. So obviously this is not a function, and why? Why? Because we see that this first element, this 3 in set A, is related to two elements here. So basically it is the breach of condition number 2 here. So it is not a function. 3 is related to two elements in second set. Or I mean, I don't need to write that, I can just write like this. Okay, let's look at the next example. And this time I have a visual example. So let's look at this. That's my set A, that's my set A, that's my set B, and instead of writing values, I'm just using the points, and that should tell us whether that should be enough for us to make a decision whether these relations are functions or not. So again, I would ask you to pause this video and see whether this relation is a function or not. And obviously it is not a function. Why? Because this element here is mapped to two elements here. I mean, oh, okay, mapping means I need to show arrows as well. So this element here in set A is mapped to two elements in set B. So again, same as the previous one. Okay, let's look at this one here. You got 1, 2. Again, I'm just using the data points, and so this maps to that, this point maps to this point, that maps to that point, and that maps to that point. What do you think? Is this a function? Again, I want you to pause the video and think about it before you answer. And my answer is that no. Why? Because there is an spare element in set A. And like this element here, it's not mapped to any element in B. In other words, this element does not have any image. There is one element A which does not have any image. Okay, let's look at one more example. This time I have this kind of relation here. This is A, that is B. I got 1, 2, 3, 4, and I got 1, 2, 3, 4, 5 points here. This is mapped to that, that is mapped to that, that is mapped to that, and that is mapped to that. Is that a function? So again, I want you to pause your video and think about it before you answer, and my answer is it is, because it satisfies both the condition. First condition is that every element should be mapped. So I can see that in A there is no element is spare, every element has been mapped. And the second condition is that every element should be mapped to at most one element, and that is what is happening here. Okay, let's look at one more example here, and this time I got these points here. So that maps to this, and that maps to this. Again, both of them map to the same image. So again, I want you to think before you answer. So pause the video and think about it before you answer, and my answer is that yes, it is a valid function because it satisfies both the conditions. Yep. So When f is a function, we normally denote f as, we say that f is a function which maps from A to B. If it is a function, if a relation satisfies both the conditions, then we normally denote it that as f such that it maps A to B. If you recall, when we were defining relation, then we also defined relation in a similar manner. So only thing that has changed here is that earlier it was a relation, now it is a function. Now we have the same terminology here, same definition. We have domain. So domain of a function is, I don't need to write here, but I'll just say domain of function is set of all first elements of the function, and in this case it is the whole A set because every element of A is used. So this is equals to A, and then range of the function A has got the same thing, same interpretation, same meaning as we had in terms of relation. So it is the set of all second elements, so of the ordered pair. So that gives you range of the function. And when f is a function, here I'm coming back here, or coming back here, just a little bit about notation here, that f is a function from A to B. I mean, just we got this here, and then we say if A comma B belongs to f, or set of f, then it means that, again, like we discussed, that f is a kind of relation, so it is just a set of ordered pairs, and this ordered pair, we are saying if this is a set of, this is a member of f, it belongs to f, then we have f, we also write this f A is equals to B, and what do we call B is the image A under f, and likewise A is the pre-image of B under f. We need to be familiar with these terminologies. Next thing is, if I mean, we already know that first element in relations and functions is normally indicated by an x, by letter x, and the second element is related is indicated with the letter y. Yeah. So as we discussed here, I'm coming back here. Suppose we are given an equation, then we could say that f is a function such that it maps x to, suppose my function is second element y is always given as x squared plus 2. So when I use that, what I'm saying here is that it maps, f is a function which maps x to x squared plus 2. Yeah, that also is a valid notation here. And other way it could be, just need to note here the different kind of arrow I have here. It's a special kind of arrow. And it could also be that f is a function which maps x to fx, and in that case you need to define fx separately. So we could say that where fx is equals to x squared plus 2. Just to keep in mind, most of you should be familiar with this, that basically it is fx is equals to y, so that we have ordered pair which consists of x and fx. Let me write here. The ordered pairs are ordered pairs will be x and fx. Okay, so there's another, we have already seen how we can determine whether a relation is a function or not, and all these were sort of roster form. We had a visual form in which mapping was visually shown with arrows, but many relations are shown as graphs as well. So we'll take a look at how to check whether a relation, when it is given in graphical form, is a function or not. So we have suppose a function which can be plotted. We have a relation, not function. We have a relation which can be plotted like this. Yeah, and the domain is defined from x equals to, this is your x and this is your y. Domain is defined from here to here. So suppose this is your A and this is your B. So domain is defined from A to B. Yeah, and within that domain we can see that because it's a straight line here, so we can see that every element is related. Every element in the domain is mapped to some value of y. And second thing is that every element in the domain on the x-axis is mapped at most to one value of y. So this is a function. Let's look at another example here. Suppose I got this kind of graph. This is x and this is y. So again, my domain is, I define my domain as x values greater than 0 or greater than 1. Suppose this is 1. Then can you determine whether this is a function or not? Think before you decide, and if you want you can pause the video. My answer is that this is not a function, because this value of x, suppose x equal to 2, it maps to two values of y. It gives me two values of y. It gives me one value of y here and gives me another value of y here. So this is not a valid function. And based upon this observation here, we have what we call a vertical line test. We have a vertical line test, and a vertical line test, as the name indicates, says that if any vertical line intersects graph at two places, then it is not a function. Yeah. So if you draw, like I draw this vertical line here, and it is intersecting my graph at two places, which means that for a single value of x here, I got two values of y. Yeah, which basically breach of the second condition of our function. So this is not a function. And vertical line test is a really important test. We can tell at a glance whether relation is function or not. So for example, if I got a function like this, and I can see that I'm saying if I got a relation like this, then yes, it is a function. If I got a relation like this, and I can see that it is not a function, and it's a quite effective and efficient method of determining whether a relation is function or not. One last thing to cover before I close. So the thing is that if domain and range both of a function are either real or subset of real values, real numbers, call it real values, real numbers, then then we call it a real function. So a function is real function if its domain and range both are either R or subset of R.